Optimization. It seems like it's everywhere these days, right?
Yeah.
I mean, we're always trying to find the best way to do things, whether it's like streamlining supply chains or, even in like discovering new drugs.
Yeah, for sure. It pops up in so many fields. The tricky part is when the problems get super complicated with tons of variables.
Exactly. And that's where things get really interesting. Because today we're going to dive into something called quantum Bayesian optimization, or QBO.
Sounds pretty intense, huh?
Yeah.
What makes QBO so compelling is that it combines the power of quantum computing with the smarts of Bayesian optimization. And that's what we're going to unpack today based on Jorgo Schneppat's essay, QBO, Quantum Bayesian Optimization for Effiziente AI.
Exactly. So in this deep dive, we're going to break down QBO. We'll start with the basics, quantum mechanics, classical optimization, and then we'll see how Bayesian optimization comes into play and how quantum mechanics can actually make optimization even better. Then we'll get into the nitty-gritty of how QBO works, its architecture, function, its potential applications, and what might be on the horizon.
Right on. Let's get started then.
Okay, so let's start with the fundamentals. Quantum mechanics. I mean, we hear this term a lot, but how does it actually play into optimization?
Okay, so quantum mechanics governs the behavior of matter at the tiniest levels, like atoms and subatomic particles. It operates on principles that are very different from the classical physics we experience every day. One of the key concepts is superposition.
Superposition, okay.
Right, so superposition means that a quantum bit, or qubit, can exist in multiple states at the same time. Unlike a classical bit, which can be either 0 or 1, a qubit can be both 0 and 1 simultaneously. And this is where things get interesting for optimization, because it allows quantum computers to explore many possibilities concurrently. It's like a massive parallel processing power.
I see. So instead of checking one option at a time, it's like checking a bunch of options all at once.
Exactly. And then there's entanglement, another mind-boggling quantum phenomena. It's this weird interconnectedness between quantum particles, where their fates are linked no matter how far apart they are. This entanglement enables coordinated operations across multiple qubits, making complex computations even more efficient.
Okay, so these quantum phenomena, superposition and entanglement, they're really the foundation for powerful quantum algorithms like Grover's and Shor's.
Precisely. Those algorithms offer the potential for huge speed-ups in certain computational tasks, and optimization is one of them.
Okay, that makes sense. So now let's shift gears a bit and talk about classical optimization. What are we actually trying to achieve here?
Essentially, classical optimization is about finding the best solution to a problem. Finding the maximum or minimum value of a function, often within certain constraints. There are two main approaches here, gradient-based and gradient-free methods.
Oh, gradient descent comes to mind.
Yeah, that's a classic example of a gradient-based method. It uses the slope of the function to guide the search for the optimal value. But gradient-based methods can struggle. When the function is really complex or bumpy, they might get stuck in local minima, which are like valleys in the function's landscape that aren't the absolute lowest point.
So they find a decent solution, but maybe not the absolute best one?
Exactly. That's where gradient-free methods like evolutionary algorithms come in. They're better at handling those really messy, nonlinear problems. But the trade-off is they can be computationally expensive because they rely on a lot of trial and error.
I see. So enter Bayesian optimization. It's a gradient-free method, right? But what makes it special?
Yeah, Bayesian optimization is pretty clever. It tackles the efficiency problem by building a statistical model, often called a surrogate model, of the function we're trying to optimize. And it does this based on the data points that have already been evaluated. This model helps predict which points are most promising to try next.
So it's not just randomly searching, it's using information it's gathered to make smarter choices about where to look.
Exactly. Gaussian processes are often used as these surrogate models, and they're great at estimating the uncertainty around the function based on the data you have.
So it tells you not only where the best solutions might be, but also how sure you are about those predictions.
Yeah, that's the beauty of it.
Yeah.
Now, to decide where to sample next, Bayesian optimization uses an acquisition function. This function balances exploration of uncharted territories with exploitation of areas where we've already found promising results.
Makes sense. So we're constantly weighing the potential of finding something even better against the certainty of sticking with something that's already pretty good.
Exactly.
Now, as problems get more complex and the number of variables increases, we run into the curse of dimensionality. I know you deal with this all the time.
Oh yeah, the curse of dimensionality. That's when the number of possible solutions explodes as you add more variables. It's like searching for a needle in an ever-expanding haystack. And things get even harder when we're dealing with noisy data or uncertainties in our models.
Right. It's like trying to find that needle when you can't even see clearly. And that's where quantum technology comes in, right?
Absolutely. This is where things get really exciting. Quantum computers, with their superposition and entanglement capabilities, offer the potential to tackle these high-dimensional problems much more efficiently than classical computers.
It's like they have a whole different set of tools for navigating that complex landscape.
Right. And it's not just theoretical. There are already quantum algorithms, like the quantum approximate optimization algorithm, QAOA, and quantum annealing, which are specifically designed to tackle those tough combinatorial optimization problems that often arise in these complex scenarios.
Okay, so we've got these powerful quantum algorithms, and we've got Bayesian optimization, which is great at handling uncertainty. It seems like they're a perfect match, especially given that current quantum computers are still prone to noise.
You got it. And that's where quantum Bayesian optimization, or QBO, comes in. It's this beautiful fusion of Bayesian and quantum approaches.
So how does it actually work? I mean, what's happening under the hood?
It's all about leveraging the strengths of both approaches. Bayesian optimization provides the intelligent search strategy, guiding us towards promising areas. And quantum algorithms come in to supercharge specific parts of the process, making it faster and more efficient.
Okay, I'm starting to see the synergy here. So can you give me a concrete example of how a quantum algorithm might enhance the Bayesian optimization process?
Sure. One of the key parts of Bayesian optimization is building and updating that surrogate model, often a Gaussian process. Some of the mathematical operations involved in that process can be pretty computationally demanding, especially as the number of data points grows.
Like inverting a huge matrix.
Exactly. But there are quantum algorithms, like the Harrow-Hasidim-Lloyd HHL algorithm, that can potentially perform matrix inversion much faster than classical methods.
And that could be a game changer for efficiency, right?
Absolutely. It could significantly reduce the time it takes to build and update the surrogate model, which is a crucial part of the Bayesian optimization loop.
Okay, so we've accelerated the surrogate model. What about the next step, where Bayesian optimization uses the acquisition function to decide where to sample next? Can quantum algorithms help there too?
Definitely. There's this idea of quantum acquisition functions, where quantum algorithms are used to optimize these functions themselves. Grover's algorithm, for example, is known for its quadratic speedup in finding a specific item in a database.
So it's like having a quantum-powered search engine to find the best next point to evaluate.
Yeah, that's a good way to think about it. It could significantly speed up the process of identifying the most promising areas to explore.
So we've got quantum-enhanced surrogate models and quantum-boosted acquisition functions. Are there any other ways that quantum algorithms can be integrated within the QBO framework?
Oh yeah, there are a bunch of possibilities. The quantum approximate optimization algorithm, QAOA, is another good example. It's a hybrid algorithm that's designed to tackle combinatorial optimization problems, the kind that are really hard for classical computers to handle.
And within QBO, how would we use QAOA?
Well, it could be used to directly find solutions for discrete optimization problems that come up during the Bayesian optimization process. It's like having a specialized quantum solver that can tackle specific types of problems that are difficult for classical methods.
I see. So it sounds like QBO is really about combining the best of both worlds. Bayesian optimization provides the overall strategy, and quantum algorithms come in as these powerful tools to accelerate and enhance different aspects of the process.
Exactly. And the beauty of it is that this approach is well suited for the current state of quantum computing, where quantum computers are still fairly limited in terms of size and error rates.
So it's a way to get practical benefits from quantum computing even before we have those fault-tolerant, large-scale quantum computers that everyone's dreaming of.
Right. And Schneppet's essay highlights several potential benefits of QBO. It could lead to a reduction in computational complexity, allowing us to solve problems faster. It could also improve accuracy, especially when dealing with noisy data or uncertain models, and it can help us navigate those vast, high-dimensional solution spaces that are often encountered in complex optimization problems.
All very promising. But I know there are still challenges to overcome, right? What does the essay say about that?
It's very realistic about the challenges. As we've mentioned, current quantum computers are still quite sensitive to noise and errors. That's a big hurdle.
So we need better hardware, more robust quantum computers that are less prone to errors.
Yes. And we also need better error correction techniques, ways to mitigate the errors that do occur. These are active areas of research in quantum computing.
And what about the limitations in terms of qubit count and coherence times? How does the essay address those?
It acknowledges that those limitations currently restrict the size and complexity of problems that can be tackled with QBO. It's like having a powerful engine, but a limited fuel tank. The essay also points out that effectively integrating classical and quantum computations, which is essential for hybrid approaches like QBO, is still a complex technical challenge.
Right, so there are definitely still hurdles to overcome, but despite these challenges, the potential of QBO is undeniable. And the essay lays out some really exciting application areas, doesn't it?
Absolutely. One area is material research. Imagine using QBO to design new materials with specific properties, like strength, flexibility, or conductivity. It could revolutionize industries like aerospace, electronics, and energy.
And I know there's a lot of interest in using quantum computers to simulate molecules and chemical reactions. Could QBO play a role there too?
For sure. Quantum computers have the potential to perform those simulations much more accurately and efficiently than classical computers. And then QBO could be used to optimize those simulations, searching for molecules with specific properties or desired energy levels.
That could accelerate drug discovery, materials design, and even our understanding of fundamental chemical processes. It's amazing. What about applications in machine learning?
Machine learning relies heavily on optimization, particularly for training models. The essay highlights how QBO could be used to optimize the hyperparameters of machine learning models, which are those settings that control the learning process.
So finding the optimal settings for those hyperparameters could lead to more accurate and efficient machine learning models.
Exactly. And the essay also points out the potential of QBO for reinforcement learning, where agents learn by trial and error. QBO could help those agents learn faster and find better solutions in complex environments.
So we're talking about potential applications in robotics, autonomous systems, and even things like personalized medicine and financial trading. What about industrial applications?
Yeah, the essay mentions areas like logistics and traffic flow optimization. QBO could help find more efficient routes for deliveries or optimize traffic flow in cities, reducing congestion and improving fuel efficiency.
And in finance, where optimization plays a huge role in managing portfolios and assessing risk, it sounds like QBO could offer significant advantages.
For sure. It could help find better ways to allocate assets, balancing risk and return, and potentially even lead to new financial instruments and trading strategies.
Okay, so the potential applications are vast. But looking ahead, what are some of the key trends and developments we should be watching for in the QBO space?
Advancements in quantum hardware are going to be crucial. The essay mentions superconducting qubits and photonic quantum computers as leading technologies in the field. Scaling up the number of qubits, improving their coherence times, and reducing error rates are all essential for QBO to reach its full potential.
So it's all about building better, more powerful quantum computers. What about research specifically focused on QBO itself?
Well, the essay highlights the importance of hybrid approaches, combining quantum and classical computing. Finding the optimal balance between these two paradigms is crucial for making QBO practical and efficient.
And it sounds like there's also a lot of interest in exploring how QBO can be combined with other AI techniques.
Absolutely. Integrating QBO with deep learning, reinforcement learning, and other cutting-edge AI approaches could unlock even more powerful and versatile optimization capabilities.
So as we wrap up our deep dive into quantum Bayesian optimization, what are the key takeaways from Schnippat's essay?
I'd say the biggest takeaway is that QBO represents a potentially transformative approach to optimization, especially for complex, high-dimensional problems. The synergy between Bayesian optimization and quantum computing could lead to significant speedups and improved accuracy.
And as we've discussed, the potential applications are far-reaching, impacting fields from materials science and drug discovery to machine learning and finance. But we also have to acknowledge the current limitations in quantum hardware and the need for continued research in hybrid quantum classical approaches.
Right. And as quantum computers continue to improve, the capabilities of QBO will grow alongside them.
So here's a final thought for you. Considering the potential of QBO and the rapid advancements happening in both AI and quantum computing, what previously impossible problem in your own field or area of interest might become solvable in the near future? What breakthroughs might be just around the corner? And that's it for our deep dive into quantum Bayesian optimization based on the insightful work of Yorgo Schneppat. Thanks for listening.
Thanks for having me.
We encourage you to explore these ideas further and see where they might lead you.